So in this lesson, lesson 7, we're investigating resonance and specifically now music in tubes, or music that comes from instruments which are pretty much just really fancy pipes. Wind instruments, of course, include the traditional brass and woodwind instruments like saxophones, and also trumpets and trombones. But the source of vibration is a little bit different for each. But the premise behind these types of instruments is that, like we can achieve resonance on strings, we can also achieve resonance in tubes or in pipes, like a pipe organ. So woodwinds and brass instruments really are just super fancy pipes, and standing waves can be created in these types of pipes. So let's just recall for a second what happens when sound reflects at both an open end and a closed end, so a free end or a fixed end. So let's recall what happens. So first, at an open end, we have a wave that comes in and hits a boundary. And if this is a free end or an open end, the wave will reflect in phase with itself. Okay, so it will reflect on the same side. The pulse will reflect on the same side. Okay, so there is no inversion in this case. It simply reflects on the same side. A closed end or a fixed end is a little bit different. Here, the wave pulse comes in, and if the boundary is something that's more dense than the medium through which the wave is traveling, say if a wave comes in and hits a brick wall, the wave will be reflected by 180 degrees, so it will be completely out of phase with itself. Its reflection will be phase shifted, and that is why we see this pulse coming back completely out of phase with itself going in. Okay. One of the really nice things is that there's some beautiful videos on YouTube, and so I've collected a few of these links, and so you can check the website and or the classroom to take a look at some of these links so that you can see exactly what this looks like, and even, perhaps help you explain why this happens. One of the major differences between wind and string instruments is the type of wave that's found in each. So with a string instrument, right, we set up standing waves, but they're transverse. So a string vibrates up and down. But in wind instruments, we find longitudinal waves. And due to the fact that longitudinal waves are very difficult to draw, we're going to be forced to model our longitudinal waves with transverse waves. So the diagrams that you're going to see are not exactly accurate because we're using transverse waves to draw them. And really, in tubes, we have sound, which is longitudinal waves, vibrating through. And we'll do an example of this. We'll take a look at an example of this using a Rubens tube as a demonstration. Standing wave patterns, this is a rule, have a node at a closed end and an antinode at an open end. So you'll remember with strings had a node at both ends. Standing waves in tubes, though, we have a couple different possibilities. We can have a tube that's open at both ends, and we can have a tube that's only open at one end. And so we have standing wave possibilities for both of these different types of tubes. So let's begin with this set of standing waves, the waves that are open at both ends. You'll see an antinode at each end, And let's note how we label the harmonics in this case. Here's our first resonant length. This is, of course, representative of the fundamental frequency. And this is what we call our first harmonic. Okay, so just like with the strings, we have our fundamental frequency and our first harmonic. We also have one node. This is half of a wave. Okay. The second resonant length, which is right here, this is resonant length number 2. This represents our second harmonic and our first overtone. Our second harmonic, which is our second resonant length, has 2 nodes. Our third harmonic has 1, 2, 3 nodes. And of course we see here this is 1. This right here is 1.5 waves, so 3/2 waves. We can build up. Fourth harmonic, you can see the pattern. It has 4 nodes. This represents 2 complete waves. We still have an antinode at both ends, here and here. And the fifth harmonic, and so on and so forth. So if we were to develop a formula, and we have a formula, what we could do is say that for 2 open ends, so an end here and an end here, we have the exact same formula that we had for 2 fixed ends with strings, is that the resonant length is equal to n lambda over 2, where n is equal to 1, 2, 3, and so on and so forth. Because here, when n is equal to 1, and we can even write that, n is equal to 1, we'd have 1/2 of a wave. Here, when n is equal to 2, we have 2/2 lambda, so we have 1 full wave. Here, we have n equals to 3, and so on and so forth. Okay, so that's for 2 open ends. Things get a little bit more interesting when we look at a wave that has an open end and a closed end. So we know that in this kind of a situation, I have to have a node at any closed end and an antinode at any open end. And so the longest wave, the fundamental frequency I can put in there, is 1/4 of a wavelength. So this right here is 1/4 of a wave. And this is what we'd call the first resonant length and what we'd call the first harmonic. Now, you'll notice that the pattern, though, isn't quite as straightforward as these pipes right here. The pipes that were open at both ends, the pattern goes 1/2, 1, 1.5, 2, 2.5, 3. But in this situation, we never get those full wavelengths. We're always kind of dealing with quarters. We have 1/4 of a wave, and then we have 3/4 of a wave, because this would be the next length that we could fit into here. Here we'd have 5/4 of a wave. Here we'd have 7/4 of a wave, and 9/4 of a wave. And to keep the consistency with what we've talked about here, where this is our first resonant length, this is our second resonant length, this is our third resonant length, and so on, the only difference is the way that we label the harmonics you'll notice that for a quarter of a wave, we have the same harmonic as we had before. But now, all of a sudden, we jump to 3/4 of a wave, and we have not the second harmonic, but the third harmonic. And we note there is no second harmonic. Okay. Then you'll notice we come down to 5/4 of a wave, and we notice there is no fourth harmonic. There is no sixth harmonic. There is no eighth harmonic when we have this type of a tube, closed at one end, open at one end. So what we have then is a situation where for one open end and one closed end, we have a slightly different formula. We have the resonant length is equal to 2n minus 1 times lambda over 4. Again, n still goes from 1, 2, 3, 4, 5, 6, 7, and so on. So these are our resonant frequencies, right, corresponding to a resonant length. But now, if you ever want to know what the harmonic number is, instead of the harmonic being the same as n, because in this case, n equals 1, that was our first harmonic. N equals 2, that was our second harmonic. N equals 3, that was our third harmonic. That's not the way it is now. If you ever want to know what the harmonic is, we look at this result that's in brackets. And this right here is our harmonic. So this is really just a labeling example, but say the third resonant length, so n equals to 3, would be 1, 2, 3, and if we say 2 times 3, right here, 2 times 3 is 6 minus 1, that gives us 5. The third resonant length is the fifth harmonic, and we can see that 1, 2, the third resonant length is the fifth harmonic. We're going to do lots of examples with this so that you get a little bit used to it, but this is the only one that's a little bit breaking from the pattern that the other two equations gave us. Here's an example of a tube that's open at both ends. An air column, open at both ends, is 1.5 meters long. The sixth harmonic is heard resonating from the column. What is the frequency of the harmonic? The speed of sound is 345. So, we know that the length of the column is 1.5 meters. We know that the sixth harmonic is what we're using, and that means, in this case, because it's open at both ends, n is equal to 6, we want to find the frequency. And so one of the things that I find very helpful to do first is to sketch the tube vibrating in the harmonic. So we can consult the chart, but we know that for n equals to 6, we're going to have 6 nodes. 1, 2, 3, 4, 5, 6, you'll see them. We also know that at the ends of the column we must have an antinode. And so I've sketched this tube in its standing wave pattern, just as it is. Here, we can now continue the problem. Ln is equal to n lambda by 2. We're choosing this because this is the equation that represents a tube that's open at both ends. We know that the tube is in its sixth harmonic, or its sixth resonant length, so L6 is equal to 6 lambda by 2. The length of the tube is 1.5, and when 6 over 2 simplifies, that's 3 lambda, giving us 0.5 lambda. Okay. We can use this value of wavelength and the universal wave equation, V is equal to F lambda. We sub in the speed of sound, which was given, and that's equal to frequency times the wavelength, and we get 690 hertz. Here's our statement. The frequency of the sixth harmonic is 6.90 times 10 to the 2 hertz. And just in case you were wondering, yes, we're going to do a few more examples in class together.